Hello, this is the next video in a playlist that I'm calling General Linear Models Design of Experiments. And this is part 5 of a little mini series that we're doing called Balanced Incomplete Block Design. And in this video, we're going to look at developing some notation and proving some properties that we're going to use in the next 2 videos about contrast in the Balanced Incomplete Block Design. Now, as a reminder, our model is y equals x beta plus epsilon, and then it's broken down into this: the mu plus the 1 vector x tau times tau, and this deals with the treatment effects, and x beta beta, which deals with the block effects. Now, the notation that we use, we're going to kind of steal from the example we used in part 1, and it was this. And so this is sort of generically what we did. There was the y vector, and the components were y1, 1, y2, 1, y1, 4. So I'm going to be a little silly and point out that there's no y1, 3, and that's because treatment 1 was not in block 3. y2, 2, y2, 3, y2, 4, and so on. Now, the big part of this notation, which I think you sometimes have to pause the video and try to figure it out on your own and rewind. It can be pretty complicated at first. So we're going to use what's called a double index for each index. So in this vector, we technically don't need both indexes. We could go y1, y2, y3, y4, y5, y6, and then just kind of remember where each of them fall in the design. But we use double indexes, that way there's no doubt. And we're going to use that for this perpendicular projection matrix on the column space of B. It is a B times K by B times K matrix. And B is the block size, K is the number of treatments within a block. But we use the IJ, comma, I prime, J prime. And so if you think about these indexes right here going down this matrix. So even though I didn't make the matrix the same size, they are, okay? So the M23 by whatever. So M23 means we go to the 2, 3. So this is 1, 2, 3, 4, 5. It's the 5th one. 1, 2, 3, 4, it'd be actually this next one. So maybe let's deal with the M1211 object. And so if you look at the indexes that go down here, the 1, 2, 1, 2 is the second one. And now you take the indexes and put them across the top. And so the 1, 2, and then the 1, 1 is the first one. So it's this element. And notice that, so the second indexes, notice it goes 1, 1, 1, 2, the second pieces, 1, 4, then it goes 2, 2, 2, 3, all the way to 4, 4. And so we use these double indexes to know the row and to know the column. And you represent it by IJ, comma, I prime, J prime. So now, next, let's introduce an indicator function. Let's call it delta. So let delta ij be 1 if I and j are equal and 0 otherwise. And the other indicator function that we have is going to be delta j be bi. And this is a set of indexes. So it equals 1 if j is in this set, where b is a set of block indices where treatment I occurs. Now, the next, probably the next half page, I think it's well, especially the next page, it's going to be a little thick in notation, but if you want to delve into the theory of this, you have to do stuff like this. So I want to flash what x beta looks like and x tau looks like. So this is from part 1, and we had treatment and block, and then this was the design matrix. So we had a column of 1s, x tau, x beta. And so we're going to look at, x beta prime, x beta, the cross products of these. And so I'd encourage you to look back at part 1 for more detail there. So here, if we take x beta prime x beta, we get the identity matrix times k. Now k is the number of treatments in a block. So it's not surprising that we get a k with a block. We take the inverse of this, it's just 1 over k times I. And then if we look at the perpendicular projection matrix of m beta, which is this, then well, this piece goes here, so the 1 over k can come out front, and then we're left with this. But then this matrix, it's a matrix of all ones, but the ones occur at the delta j prime index. So these are actually block indices. So if we look at this, so it's when the block indice going down equals the block indice going across that we get a 1. And that's what this represents. And really the best way to do that is to write out an example. Do a simple, silly, small number example and look at that. Now x tau, the matrix x tau, can be broken into A columns. We call them x1 tau, x2 tau, etc. And so this matrix can be thought of as, now notice that the number of rows is b times k. So we can index it like this, but going across there's only A columns. It's not the same number. So we index it ij, going the first indice, that tells us, you know, what row, and then m tells us what column, and the tau of course reminds us that we're in the x tau treatment. And so these are only 1s and 0s, and it happens to be a 1 when I is equal to m. So we can represent this matrix as delta IM, and depending upon what column we're in. Now here, if we look at the cross product of x m tau times x m tau, so we're going to, you know, since it's the same vector, we're going to get squared things. And we're going to sum over the ij index, right? Because that's how many rows there are. That's how, and so this xij is what we're summing over. And then of course, m and tau is the same because it's the same vector and it's squared. But this can be written in delta form, delta im squared. But delta is either 0 or 1, so squaring it doesn't change it. So I put an x right there. We don't need it. And then notice there's no j here, but we have a j index. And the j in here, so the bi is the treatment indexes or the blocks that treatment I is in. And there's r blocks because it's replicated r times. So that's why we get the R out front, and then we're still indexing over I, but there's only one time where I and M equal. That's when I is M, so that's 1, the rest are 0, so it's just R. Now I'm going to say clearly when the columns are different and you do this cross product, it's 0. And this is one of those really dull moments. Once you write it out and go through it, it's so simple, it's 0. But let's prove it in this thicker notation. So let's do the cross product of 2 columns in x tau. So the nth column and the nth column. So when we product this, remember the first component and first component is product together. And then it's added to the second and the second, and the third and the third. But remember, to go down this vector, we're using the double indices. So that's why there's 2 indices. And it's the same, right? The same component is multiplied by the same component there. So I and j have to equal, and we're summing over them. And it's the nth column and the nth column. But these can be represented by delta in, delta im, and notice there's no j here. So we're summing this r times. That's where we get this. Now this sum, delta is 0 or 1, and it's only 1 when I is in. But when I is in, this is 0. And this is 0 and only 1 when I is m, but when I is m here, this is 0. So this is 0, and we get the same. So now I'm going to do two more sort of thick notation examples, and then we'll just start listing more of the properties associated with this, and you can do the rest on your own. Now x tau prime x tau is r times I. Now r is the number of replications of a treatment, and so it's not surprising that we see an r when we're dealing with x tau. Now m beta times m tau, so this is a perpendicular projection matrix. It's a BK by BK matrix, and this is a BK by 1. It's a vector. Okay, so this matrix can be represented by IJ, right? That tells us what row, and then here it's only one column. It's the mth column, so that's why we have an M right here. Now, so generically Cij is this, right? So it's the ijth row times this, and so this is what this represents. So ij stays the same, and we're summing over that second index, right? We're going across that row, different columns, and that represents different columns. And then ij, of course, we go down, but the row stays the same, but the first column represents the first component. Second column represents the second component. That's why I prime j prime is equal to I prime j prime in our vector. So this is generically how Cij comma m is represented. But then we said that m is generically this 1 over k delta jj, and a column in tau. So I probably should have a tau right there. Darn it. It's a 1 or a 0, and it's delta I prime m. I'm trying to find a pen here. Oh, I guess I don't need it on the delta, but I needed it here. Darn it. Okay, so then when we look at this, we sum this first, so there's no j component here. Let's sum over I prime first. Sorry for that brain cramp. Now, since there's only one I prime here, and this is 0 or 1, and it's only 1 when I prime gets to m, right? So there's only one time that is 1. It's when I prime is m. So it's like we didn't add it, and it goes away. So what's left is j and this right here, right? 1 over k. And now we're summing j prime through this set of indexes bi prime. And so this is 1 when j and j prime are equal, but they're only equal when j is in this set, right, of m. Yep. Okay. So that's it for this. Now I'm just going to list some properties. I'm going to let you prove them on your own. So if we take a column, the same column, times m, okay, and really that should be m beta. I don't know why I didn't do that. So let's put an m beta here, m beta, m beta, m beta, m beta. So then this we can create a vector. Right? M is idempotent, so m is m times m. And now a vector, you get squared things. And we said this was 1 over k times this delta j. And so these are all, and so this represents R. It's the number of times the treatment is replicated. And so that's where we get this R. Now, if we do this with not the same vector, so in an mth column of tau times m beta yeah, sorry for that there. Then when we multiply these together, it's only going to hit, it's only going to be non-zero the number of times n and m appear in the same number of blocks. And we called that number lambda. So where lambda is how many times n appears with treatment m in the same block. And so that's how we get lambda k. So when we look at this vector, this column of tau times m times x tau, we end up with a matrix, right? So if we just look at the first column, column 1, that it tells us that we're going to get lambda k. And it's going to be lambda k each time until we get to the nth column of this matrix, and then it's going to be rk. All right, so now this one last property and we're finished. So about 10 lines. And this next property we are going to use in the contrast videos. It's going to actually be a key component that we'll point back to. So here we have I minus m beta x tau. So in this m beta x tau is what all these previous things represent. And here we're summing the columns of the tau matrix. We're going to put an arbitrary constant in front, and then we're going to use k, lambda, and a. A is the number of treatments, lambda is the number of times treatment n appears with treatment m, k is the number of treatments within a block. So what I want to do is take this junk and this times that, and then subtract it from this, multiplied together. So that first one comes down, right, the x tau, and then this junk is here. And then over here we have the same. And we're going to look at them separately. So let's look at the first one and just write it out. So we're going to do the sum, right? So the k lambda a is over here, and then I is 1, C1, x1 tau, x tau, right? All the way to CA, XA tau. But we said this creates a vector when they're the same. So this is component 1, this is the first column. With the first column, we get R, right? And the C carries along. And then when they're not the same column, right here, when they're not the same column, we get 0. But then we have to do that for each one of these. This creates a row vector. So when A is not equal to the first column, so we get a 0, and it's actually 0 on all of them except for the last one. And then we carry along the CA. Now we add all these vectors up, and we get this. So the R can be factored out, which is this, and then all the other components add to this, C1, C2, all the way to CA. Now this second piece, let's write out, I ignore the minus for now, but let's write out what this sum is. So let I equal 1, and we get this, and I equal 2, all the way to I equal m. And then this creates a row vector, and whenever this column is equal to this column, in this matrix, we get R divided by k, and when it's not, we get lambda over k. And then we go all the way across, and it's the same way. So we get lambda over k, except for the 8th column of this matrix, we get rk. Now, the k can be multiplied in, which cancels with all these k's. The lambda can be multiplied in, and it cancels with all the lambdas, but this one, it leaves a divided by. So we get 1s in all the other components. We get a lambda. Now let's add them, right? So the C1 goes into each component. The CA goes into each component. The C2 goes into each component. And so when you add those, This is actually the sum from I equals 2 to n, and it's and then this is this and so we're missing 1. It's I equals 1 to a minus 1. So if we add an extra sum, then we have to subtract it, and that's where the minus lambda over lambda, which is minus, and then we get a minus CA. So if we added an extra CA here, we have to subtract 1. And the same way here. So this is I equals 2 to A. So if we put a C1 here, we have to subtract C1 here. And so otherwise we add it. Now when we add, so we multiply the A into each component, and then we add components. So this component adds to this, and all the way down to the 8th component adds to this. Now we subtract them. We subtract these two quantities. And I'm going to let you do this on your own because the video is starting to run a little long. In the first component, we get C1 minus 1 over A times the sum of the C's. And all the way to the 8th component, we get CA minus 1 over A times the sum of those C's. And then we're finished. And this property we're going to use heavily in one of the theorems to prove a theorem about contrast. But a big note here is if we add these components, so this plus this plus this plus this, it actually sums to 0, right? So we're adding C1, C2, C3, so we get the sum of the C's, and then over here we get a minus, and we're adding the same minus, and so the A's cancel, and the sums end up being 0. And another property that we're going to take note of, if we already go into this saying that the CI's must sum to 0, then this vector, it becomes C1, C2 to CA. Okay, so that's all I have for this video. It's a little long, but it's necessary if you want to dig into the theory of incomplete block designs, specifically balanced incomplete block designs. Well, I hope you enjoyed it. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.